I missed it.
Okay, guys, this is 5.1 day 2. We have already got all of the notes part or note side of things done. We just need to is just to find or how to use all of those 4 different boxes. I think it was 3 boxes or 4 boxes. And I hinted at yesterday that these topics, this whole idea of identities, is like a chess game. It's that idea that you can't just move in the moment. You need to say, what can I do? And kind of forward think it in your head before you actually do it. And kind of visualize what would happen. It saves yourself about 3 times the amount of work because you're less likely to run into a roadblock. You're more likely to make more connections this way. And so there are a couple strategies here, and we're going to go through a couple of these strategies. Obviously, forward thinking is one of them. 2 would be anytime you see a squared function, you're thinking the Pythagorean identities, switch it out. You're going to rewrite, as the problem here says, in sine and cosine. We're going to get common denominators, as in adding or subtracting fractions, which is another one. We are going to get rid of fractions. That's another one. And so there's several different things, and some more are going to be taken into account here. So in this case, when in doubt, you're looking at a problem and it's made up of a lot of different types of functions. I say, go ahead and write them in terms of sine and cosine. It'll make your life easier. And so I look at this. A secant is really what? 1 over cosine x. Minus, what's tangent? Sine over cosine. So sine of x over cosine x. And sine of x is just sine of x. Now look what I am going to do. I put this over 1. I put it as sine of x over 1 because anything can be written over 1. The reason I do this as well is the fact that I know that I have fraction times another fraction, and when you do that, you multiply what? Across. Top times the top, bottom times the bottom. So when I actually make that move, it'd be 1 over cosine x minus sine squared x over cosine x. I got it. Now have a common denominator, and I need that. So when I put those together with the common denominator, isn't that just 1 minus sine squared x all over cosine x? I'm not done. You might be thinking, hey, everything's in sines and cosines, yeah? But you're not done unless you can't go any further. And in this case, there's something up there that looks like, hey, I might be able to change that into something else. What is it? It is the 1 minus sine squared x. Hopefully, guys, you're looking at that going, wait a minute. Sine squared x plus cosine squared x is equal to what? 1. So if I happen to solve that, or should I say, wait a minute, I got a 1 on the right, I got a sine on the left, could I subtract sine to the other side?
Yeah.
And so if I do that, wouldn't that be cosine squared x is 1 minus sine squared x? And isn't that the top? Which means I should be able to write it as? Oh, so you're saying cosine squared x over cosine x. Now wait a minute, when I have something squared divided by itself, Doesn't the square in the bottom cancel out? Leaving you with? I think that would be the most simplistic sine or cosine version I could have. So this complicated looking expression up here can be written as cosine x.
Why can't you just say cosine x if you know it?
You don't know that. Did you know that was equal to cosine x? Not until we solved it, right? So, it's relevant because we are all about using steps, deductive reasoning, to change something into something easier for us to use.
You can use this with soccer.
Yes. So when you're presented with the ball following the arc of a secant x minus tangent x sine x, you can say, wait a minute, that following just the same trajectory of a cosine x. That's easy. Should be done in your head.
I've done it in my head.
Okay.
Just stop the game and work through the problem real quick in my head.
No, you just do that in your head, real on the fly.
And then you're like, oh, it's cosine x. And you score.
Yeah. Okay.
Where are we on the outline?
Almost at past Bob. Yeah, I'll let you know.
Okay. Next one. Another technique to simplify is just simplify by factoring. So when you're stuck, you try switching the sines and cosines. You try switching to other forms. And one of them now is factoring. Now I look at this and I may not think of factoring at all. Because what's going to happen is they're going to give you homework and they're just going to say simplify. They're not going to say by a certain task. You are going to have to figure this out on your own. But since it tells us that it wants by factoring, as it stands, what's the only thing I can factor out of this? What's the only thing that's common in both? They're both negative. So I could take a negative 1 out. Do you guys agree? Mm-hmm. But that really doesn't help me much because I'm left with this weird thing. And a function that's squared. Maybe that might be an option. And then secant. There should be two parts right now that are kind of like ringing a bell. Something that needs to be addressed. Obviously, I think one of those things would be possibly tangent squared. I could change that. But doesn't this thing look familiar too?
Yeah.
It's a cofunction. And remember the link for cofunctions, just the way you say them. What is that function right here? What do you call that? Cosecant. So what's its cofunction? Secant. Sine and cosine are cofunctions. Secant and cosecant are cofunctions. Tangent and cotangent are cofunctions. So guess what? The cofunction to cosecant of this is just secant of x. And it's still negative. Minus tangent squared x secant x. Go back to your cofunctions from yesterday, and you will see the link that it's always of the other angle.
Oh, yeah.
So pi over 2 is really like 90. So 90 minus whatever x or theta is the same as the other function. Remember, sine of 30 is the same thing as cosine of 60.
Yeah, that's right.
Now,
What if we had secant? Does that mean we have to double?
so what do I have in common now in both of those? No. X, you can't take x out because x is inside the function. Secant. But also, you can't lose the fact that what else was there? A negative. So I'm going to factor out a secant x, or negative secant x. So if I take and divide negative secant x by another negative secant x, I get 1. A negative tangent squared x secant x by a negative secant x. Negative makes a, and then the secants will
Cancel out.
cancel out. Huh. So I factor, but I got this thing inside. Obviously secant x is secant. That's pretty easy. Or 1 over cosine. But could possibly this thing be changed out?
Yeah, I think you.
Isn't that another one of those identities?
Would be secant squared x.
Why is it secant squared x? What's the identity? Isn't it tangent squared x plus 1 equals secant squared x? Just because it's 1 plus tangent, it's the same thing as tangent squared plus 1. So therefore, I can switch that 1 plus tangent squared out with secant squared x. And when I multiply those two together, I get negative secant cubed x. Done.
Isn't that t squared?
No, because you're not. Remember, it's not the same. What we're really writing. That was bad parentheses. This is really secant x squared. It's on the whole entire function. And remember, we move it in so people don't get it mixed up because it's not on the x. So it's secant x with a square on it times another secant x, which is really secant x to the third power.
Where's the 1 plus tangent squared?
Now, I'm going through this. I'm helping you guys along. I'm giving you guys prompts here. A lot of times I hear, they're pretty easy when you go through them and you help us. But when I do it on my own, it's not as clear. It's about as clear as mud. And again, you have to be okay with failing. You need to be okay with getting to a wall and saying, I can't do this. I need to back up, retry again. But when that happens, do not just try to erase it and recopy things you've done. You're going to end up making the same mistake. Cross it out completely, boom, like this, and restart the problem and try to go with a different method. Change something else. It's kind of like when you write a paper and you read it yourself, your brain's fixing anything that looks wrong or reads wrong. But as soon as someone else reads it, they can pick up on some of those mistakes. Okay? So be very careful on that. Hence, you're going to have a lot of time tomorrow to work on our work. This one, I'm actually not going to do the second example. We're only going to do the first example, so let me get that out of the way. Another technique is to simplify by combining fractions. But the only way to combine fractions is if they have a common denominator. So therefore, can't cross multiply. We're not multiplying, or there's no equal sign between them. So, can't flip. So, you need a common denominator. To get a common denominator, guys, you need the LCD. Least common denominator. Now, remember there are some rules for the least common denominator. It's all about the first guy. First of all, you factor all the denominators. The first guy gets to bring everything in his denominator. And after that, you keep multiplying things in that are multiples or things that were not there. And now, in this case, we have a 1 plus sign of x. There's a plus sign there. That means that whole entire thing, this whole entire expression on the bottom, is the factor. I can't break it down. Can't make it any smaller. Cosine, also the same thing. These are already broken down. Which means now I need to go and multiply the tops and bottoms by the missing pieces. So I should multiply cosine x to the top and bottom over here, right? And on the other side, it's going to be 1 plus sine x to both the top and bottom. Now, with past experience of doing these, I'm going to let you guys in on a little secret. Do not, in the beginning, multiply your denominators together. Like physically do the actual multiplication. Leave them separated, but yet show that they're multiplied. The reason is that because we're dealing with identities, there's a lot of times we're going to switch things up, factor things, all of that, that's going to end up resulting in the exact same factor on top that we'll be able to cancel one of those. Maybe both of those. You just never know. So, I think everybody would agree that so that means that the bottom would become cosine x times the quantity 1 minus sine x, or 1 plus sine x, yes? The top, cosine times cosine, cosine squared x. And then you have to FOIL. Now, you should know the pattern for that. But if you don't, 1 times 1 is 1 times sine x. And then you got sine x times 1. So you got 2 of them, right? And then sine x times sine x. Or sine squared x. Is everybody okay with that? Now, what we have to do is we have to simplify that. There should be some things in there that you just don't seem to care for or like about it. Or saying, maybe I could change that. There's a couple different ways we can handle it. What are those places or things that we don't like? Cosine squared x and sine squared x. There's a quick method and a longer method. Well, let's do the longer one, okay. So, the longer one. Wouldn't you guys agree that I could change cosine squared x to equal 1 minus sine squared x? That goes back to that Pythagorean identity. We've already used this one, I think. Right? So that means that I could take this cosine out. I'll change colors so you guys can see it. That means this is 1 minus sine squared x. I'll turn back to red. And then it's plus 1 plus 2 sine x plus sine squared x all over cosine x 1 plus sine x. What's going to happen with... Do I even need those parentheses, first of all? No. So then that would be 1 plus 1, which is 2. Wait a minute. That's a negative sine x squared and a positive sine squared x. Yeah, they're going to cancel. So that leaves me with plus 2 sine of x all over the bottom, or denominator. But wait a minute. There's something on top now. What do they have in common? So couldn't I take the 2 out? Factor that? What do I get?
1 plus sine x. And it's the same thing. So it's 2 over cosine x.
Boom. Those cancel, leaving you with 2 over cosine x. But actually, I don't like that because cosine's in the denominator. It's really what? I'm going to bring it up.
How do they cancel if they're both positive?
They're both the exact same thing multiplied to the top and bottom. They're gone. Cancel them. It's like 3 over 3. It's 1. What is 2 over cosine? If I bring cosine to the top, what does it become?
2 cosine x.
No, it's on the bottom. It's 1 over cosine. If I bring it to the top, it's the reciprocal, which is secant x.
Oh, yeah.
So that whole entire complicated expression can be represented by 2 secant x. I think it's pretty cool stuff. Hey guys, remember I said there was a long way and a short way?
Yes.
And we decided to go the long way? That other way, guys, is, can't I just take these What's cosine squared plus sine squared? It's 1. And if all of this equals 1, and 1 plus 1 is 2 plus 2 sine x, I jump all the way down, I skip the step. So sometimes you see connections and you go with it. Other times you don't see it, you're fumbling your way through and you get it. So there are sometimes more than one way to do a problem. Don't ever make fun of somebody or tell someone they're doing something wrong because they took more steps than you. The end answer is 2 secant x. If you both get there, you both get it. So, the next one is all about getting rid of fractions. If I rewrite this that does not have a fraction, it'll be its most simplified form. Part A is a 2-step problem. Wait a minute, didn't we just write something about that denominator on the last slide?
Yes.
We said that 1 minus sine squared x is equal to?
No.
Cosine squared x. And when you divide something by itself, it equals? 1. Done.
Wait, how do you find
Guys, I also could have expanded cosine squared x to 1 minus sine squared x, and therefore the top and bottom would have also resulted in the same exact thing. So those are pretty fun. Those are easy. 1, 2-step problems. Part B, not so much.
Can you just multiply?
Part B, there is a fraction, obviously. There's a couple options to work with this one, but just remember that when working with a fraction, what you do to the bottom, I have to do to the top. I can't square a fraction, that will change it. But I can multiply or divide. And so, I propose that you multiply the top and bottom by not the denominator, but by its conjugate. So therefore, I'm not multiplying the top and bottom by secant x plus tangent x. I'm going to multiply the top and bottom by secant x minus. You guys should have done something like this last year. This idea works with other functions as well. Those other functions would be things like square roots. Anytime you had a square root with a plus or minus of something in front of it, you always multiply by its conjugate. I's, 2 plus 3i in the denominator, you would multiply by 2 minus 3i to get rid of it. Because guess what? The denominator, guys, is the sum and the difference. And the sum and difference of binomials multiplied together give you the difference of squares. And so you're left with 4 secant x minus tangent x all over secant times secant is secant squared x. I can do minus a tangent secant, add a tangent secant, which then they disappear, and then it's minus tangent squared x. No. You mean to distribute the 4?
Yeah.
We could distribute the 4. So 4 secant x minus 4 tangent of x. But wait a minute. Doesn't it seem to be a square of a function and another square of a function? Do we have formulas to get rid of one of those or both of those?
Well, definitely the tangent squared x.
Tangent squared x for sure. Secant as well. All 6 of them are there some way, shape, or form. Do we have any of them that are just listed as right there? Let me get the eraser out.
Yeah, the second one. I didn't miss a lot.
Look at that. Secant squared in the middle.
Wait, where?
This one right here. Isn't that secant squared theta is equal to tangent squared plus 1?
They get there.
Oh, yeah, that's here.
Oh. Okay. So we can do that one. So therefore, whoops. All this over here. So this becomes secant squared is tangent squared x plus 1 minus tangent squared x. Because secant squared is tangent squared plus 1. Hey, wait a minute. What's happening to the tangents? Gone. And it's all over 1. So the answer is 4 secant x minus 4 tangent x. No fractions. Even though tangent and secant would be considered to be 1 over cosine and sine over cosine, but because I'm using the appropriate function, the fraction's not there anymore. So, this is a lot of homework. It's 16 problems.
That is a lot, Mr. Patrick.
It's a lot because of the type of problems they are. I want you guys to attempt them tonight. And tomorrow, we will have time in class to work on these. I want us to struggle. I want you guys to actually persevere through these. And I want you guys to try different things in a low-stress environment.
He wants to fail.
So, have a good night.